Summary. In this chapter we have discussed a wide range of problems that can occur in distributed systems, including, whenever you try to send a packet over the network, it may be lost or arbitrarily delayed. Likewise, the reply may be lost or delayed, so if you don't get a reply, you have no idea whether the message got through. A node's clock may be significantly out of sync with other nodes despite your best efforts to set up NTP. It may suddenly jump forward or back in time, and relying on it is dangerous, because you most likely don't have a good measure of your clock's error interval. A process may pause for a substantial amount of time at any point in its execution, perhaps due to a stop-the-world garbage collector, be declared dead by other nodes, and then come back to life again without realizing that it was paused. The fact that such partial failures can occur is the defining characteristic of distributed systems. Whenever software tries to do anything involving other nodes, there is the possibility that it may occasionally fail, or randomly go slow, or not respond at all and eventually time out. In distributed systems, we try to build tolerance of partial failures into software, so that the system as a whole may continue functioning even when some of its constituent parts are broken. To tolerate faults, the first step is to detect them, but even that is hard. Most systems don't have an accurate mechanism of detecting whether a node has failed, so most distributed algorithms rely on timeouts to determine whether a remote node is still available. However, timeouts can't distinguish between network and node failures, and variable network delay sometimes causes a node to be falsely suspected of crashing. Moreover, sometimes a node can be in a degraded state. For example, a gigabit network interface could suddenly drop to 1 kb/s throughput due to a driver bug. Such a node that is limping, but not dead, can be even more difficult to deal with than a cleanly failed node. Once a fault is detected, making a system tolerate it is not easy either. There is no global variable, no shared memory, no common knowledge or any other kind of shared state between the machines. Nodes can't even agree on what time it is, let alone on anything more profound. The only way information can flow from one node to another is by sending it over the unreliable network. Major decisions cannot be safely made by a single node, so we require protocols that enlist help from other nodes and try to get a quorum to agree. If you're used to writing software in the idealized mathematical perfection of a single computer, where the same operation always deterministically returns the same result, then moving to the messy physical reality of distributed systems can be a bit of a shock. Conversely, distributed systems engineers will often regard a problem as trivial if it can be solved on a single computer, and indeed a single computer can do a lot nowadays. If you can avoid opening Pandora's box and simply keep things on a single machine, it is generally worth doing so. However, as discussed in the introduction to Part Roman 2, scalability is not the only reason for wanting to use a distributed system. Fault tolerance and low latency by placing data geographically close to users are equally important goals, and those things cannot be achieved with a single node. In this chapter we also went on some tangents to explore whether the unreliability of networks, clocks, and processes is an inevitable law of nature. We saw that it isn't. It is possible to give hard real-time response guarantees and bounded delays in networks, but doing so is very expensive and results in lower utilization of hardware resources. Most non-safety critical systems choose cheap and unreliable over expensive and reliable. We also touched on supercomputers, which assume reliable components and thus have to be stopped and restarted entirely when a component does fail. By contrast, distributed systems can run forever without being interrupted at the service level, because all faults and maintenance can be handled at the node level, at least in theory. In practice, if a bad configuration change is rolled out to all nodes, that will still bring a distributed system to its knees. This chapter has been all about problems and has given us a bleak outlook. In the next chapter we will move on to solutions and discuss some algorithms that have been designed to cope with all the problems in distributed systems. Matthew P. Grosvenor, Maltschwarzkopf, Ionel Gog, et al. Queues don't matter when you can jump them. At 12th Usenix Symposium on Networked Systems Design and Implementation in SDI, May 2015. Brandon Phillips, Etct. Distributed Locking and Service Discovery, at Strange Loop, September 2014. Naohiro Hashibara, Xavier D. Fago, Rami Ierd, and Takuya Katayama. The Letter 3D5 Accrual Failure Detector, Japan Advanced Institute of Science and Technology, School of Information Science. Technical report is RR 2004-010, May 2004. Cisco, Integrated Services Digital Network, docwiki.cisco.com. InfiniBand FAQ. Mellanox Technologies, December 22, 2014. James C. Corbett, Jeffrey Dean, Michael Epstein, et al. Penner. Google's Globally Distributed Database. At 10th Usenix Symposium on Operating System Design and Implementation OSTI, October 2012. Nelson Minar, A Survey of the NTP Network, alumni.media.mit.edu, December 1999. Timekeeping in VMware Virtual Machines. Information Guide, VMware, Inc., December 2011. MyFID Roman 2/MyFIR, Regulatory Technical and Implementing Standards, Annex I Draft, European Securities and Markets Authority, Report ESMA/2015/1464, September 2015. Sandeep Kulkarni, Murat Demirbaz, Deepak Madhba, et al. Logical Physical Clocks and Consistent Snapshots in Globally Distributed Databases, State University of New York at Buffalo, Computer Science and Engineering Technical Report 2014-04, May 2014. Christopher Clark, Kerr Fraser, Stephen Hand, et al. Live Migration of Virtual Machines, at 2nd Usenix Symposium on Network Systems Design and Implementation NSDI, May 2005. Martin Maas, Tim Harris, K.R. Stojanovic, and John Kubietovich, Thrash Day. Coordinating Garbage Collection in Distributed Systems, at 15th Usenix Workshop on Hot Topics in Operating Systems Hot OS, May 2015. Any Sursuter, HBase and HDFS. Understanding File System Usage in HBase at HBaseCon, June 2013. Brian Palmer, How Complicated Was the Byzantine Empire? Slate.com, October 20, 2011. John Rushby, Bus Architectures for Safety Critical Embedded Systems, at First International Workshop on Embedded Software MSoft, October 2001. Andrew Miller and Joseph J. Laviola, Jr., Anonymous Byzantine Consensus from Moderately Hard Puzzles, A Model for Bitcoin, University of Central Florida, Technical Report CSDR 14-01, April 2014. James Mickens, The Saddest Moment, Usenix Login, Logout, May 2013. Evan Jones, How Both TCP and Ethernet Checksums Fail, evanjones.ca, October 5, 2015. Flavio P. Junquera, Dude, Where's My Metadata? FBJ.me, May 28, 2015. J. Krebs, A Few Notes on Kafka and Jepsen, blog.empathybox.com, September 25, 2013. Frank McSherry, Michael Izzard, and Derek G. Murray, Scalability, but at what cost? At 15th Usenix Workshop on Hot Topics in Operating Systems Hot OS, May 2015. Chapter 9 Consistency and Consensus. Is it better to be alive and wrong or right and dead? J. Krebs, A Few Notes on Kafka and Jepsen 2013. Lots of things can go wrong in distributed systems, as discussed in Chapter 8. The simplest way of handling such faults is to simply let the entire service fail, and show the user an error message. If that solution is unacceptable, we need to find ways of tolerating faults, that is, of keeping the service functioning correctly, even if some internal component is faulty. In this chapter, we will talk about some examples of algorithms and protocols for building fault-tolerant distributed systems. We will assume that all the problems from Chapter 8 can occur. Packets can be lost, reordered, duplicated, or arbitrarily delayed in the network. Clocks are approximate at best, and nodes can pause, for example, due to garbage collection or crash at any time. The best way of building fault-tolerant systems is to find some general-purpose abstractions with useful guarantees, implement them once, and then let applications rely on those guarantees. This is the same approach as we used with transactions in Chapter 7. By using a transaction, the application can pretend that there are no crashes atomicity, that nobody else is concurrently accessing the database isolation, and that storage devices are perfectly reliable durability. Even though crashes, race conditions, and disk failures do occur, the transaction abstraction hides those problems so that the application doesn't need to worry about them. We will now continue along the same lines and seek abstractions that can allow an application to ignore some of the problems with distributed systems. For example, one of the most important abstractions for distributed systems is consensus, that is, getting all of the nodes to agree on something. As we shall see in this chapter, reliably reaching consensus in spite of network faults and process failures is a surprisingly tricky problem. Once you have an implementation of consensus, applications can use it for various purposes. For example, say you have a database with single leader replication. If the leader dies and you need to fail over to another node, the remaining database nodes can use consensus to elect a new leader. As discussed in Handling Node Outages on page 156, it's important that there is only one leader, and that all nodes agree who the leader is. If two nodes both believe that they are the leader, that situation is called split brain, and it often leads to data loss. Correct implementations of consensus help avoid such problems. Later in this chapter, in Distributed Transactions and Consensus on page 352, we will look into algorithms to solve consensus and related problems. But we first need to explore the range of guarantees and abstractions that can be provided in a distributed system. We need to understand the scope of what can and cannot be done. In some situations, it's possible for the system to tolerate faults and continue working. In other situations, that is not possible. The limits of what is and isn't possible have been explored in depth, both in theoretical proofs and in practical implementations. We will get an overview of those fundamental limits in this chapter. Researchers in the field of distributed systems have been studying these topics for decades, so there is a lot of material. We'll only be able to scratch the surface. In this book we don't have space to go into details of the formal models and proofs, so we will stick with informal intuitions. The literature references offer plenty of additional depth if you're interested.